All right, welcome back. Last time, I had a couple of questions that I wanted to address, and so I've written them down here, just sort of paraphrasing the way I wrote them last time. So we've got some set S, a collection of vectors in a vector space V. The first question, if we have some vector U in capital V, does that vector lie in the span of our set S? So there's question one. And question two, is S a spanning set for our vector space V? Last time, sort of the last portion of the lecture, we were addressing question one, and now what I want to do is take up question two. So let's start with an example here. So I want to work in M22, so remember that is the vector space consisting of all 2 by 2 matrices. So in M22, let S be this collection of matrices that I'm going to call A1 up through A44, and now I need to tell you who they are. So where A1 is just going to be the identity matrix, so 1, 0, 0, 1. A2, 1, 0, 1, 0. A3 is the matrix of, A3 will be 0, 1, 1, 0. And A4 is going to be the matrix, it'll have a 1 up in the upper right-hand corner. Okay, so here's our setup. We've got our vector space M22, we've got our set S consisting of these 4 matrices, and then our question is S a spanning set for M22? To answer this question, what I need to do is take an arbitrary vector in our vector space. So in this case, I want to take an arbitrary matrix and decide, can that arbitrary matrix be expressed as a linear combination of these 4? So for our solution, let's call it capital B. So let's let B equal A, B, C, D. So I'm choosing a generic matrix in our vector space right now. So now, come on. Every once in a while the lights are going to go out. Okay, so here's my matrix, and now to answer this question, we need to decide whether the following equation has solutions. So I want to set this equation of x1 times a1 plus x2 times a2 plus x3 times a3 plus x4 times a4, set that equal to b and determine whether there's a solution. Is there an x1, x2, x3, and x4 that solve this equation? All right, so let's actually write this out now. This would mean x1 times the identity matrix plus x2 times 1, 0, 1, 0 plus x3 times 0, 1, 1, 0 plus x4 times 0, 1, 0, 0. Oh, am I going to run out of room here? That's my marker here. I think I can squeeze it in A, B, C, D. Okay, let me just check. Yeah, it looks like it's still in the shot. All right, so here's the equation that I need to solve, and I'd like to actually combine all the stuff on the right-hand side now, on the left-hand side, into a single matrix so we can see what we're looking at. So let's see, we'll have an x1 plus x2, then we'll have an x3 plus x4. We will have an x1 plus x3. And then we'll have an x1. Let's make sure I got all this right here. Yes, there's an x1, x2. No, sorry. This lower one right there should be an x2 plus x3. All right, and that needs to equal the matrix A, B, C, D. Well, this creates a linear system. Let me write out what this linear system is. x1 plus x2 has to equal A. X3 plus x4 has to equal B. x2 plus x3 has to equal C. And x1 has to equal D. All right, now we have a linear system. What I like to do is replace that with the augmented matrix that corresponds to this system. So I'll have a 1, 1, 0, 0, A, and a 0, 0, 1, 1, B, and a 0, 1, 1, 0, C, and a 1, 0, 0, 0, D. Okay, so there's the corresponding augmented matrix. And one thing we know, this system, so the question now is whether this system is consistent. So maybe let me write that out. So question now is the system consistent? If the system is consistent, that tells us that there is an x1, x2, x3, x4 that solve this, which means that B lies in the span of our set capital S, which means that S is a spanning system. If, for some choice of A, B, C, and D, there is no collection of x1 through x4 that satisfy it, then we would say it's inconsistent, which means that we do not have a spanning set. Now, okay, we have various ways to decide whether our system is consistent, but we have a special case here where I've got a square matrix here. So what I want to do is go like this. So since the determinant of the coefficient matrix of 0, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 0. I'd like to look at the determinant here. And I'm going to expand about the bottom row there. That's the obvious choice. So let's see, that determinant is going to equal, so it'll be 1 times the determinant of that little 3 by 3 there. And so that will be 1 times minus 1. Right, so the determinant is equal to -1. The system is consistent. In fact, for every choice of A, B, C, and D, there's a unique choice of x1, x2, x3, and x4. So in fact, we actually have unique solution. The uniqueness is not necessary. Right? As long as we have a solution, the system would be consistent. So I just put that in parentheses here. So since the determinant is equal to -1, which is not equal to 0, and that was really the important part here, that tells us that this matrix right here is invertible, and so by computing the inverse, we could actually see who the solution is. So, conclusion. Span of S, I guess I don't need to capitalize that, but span of capital S is equal to M22. I went through a lot of details there, went through all the steps. Well, let's try another example here. But I want to elaborate. Spanning sets, this whole idea of span can be kind of confusing when you first see it. I remember when I first learned it, I just could not, it just did not sink in for me. So I just want to elaborate. What exactly does this say? It says that every, so let me write that down. So that is every matrix let's say A, B, C, D in M22 lies in the span of S. So everybody in M22 is a linear combination of the matrices in S. Okay, so hopefully I'm not belaboring this too much. but I just remember having a difficult time understanding what this whole idea of span was. So, I'm going to write down what you could consider sort of a general procedure. So let's call this identifying spanning sets. So step one, let's let S equal V1 up through V sub k. Be a set of vectors. In V, and let X be arbitrary. So what we're trying to do, and I'm going to double underline that word arbitrary right there. The question is, do we have a spanning set? Is the span of S equal to V? To answer that, right, so we've got our set that is our potential spanning set. And then we choose, what we want to do is we want to choose an arbitrary vector, and I should say arbitrary, be an arbitrary vector in capital V. So when I say arbitrary, I mean I don't want to put some actual numbers in there. Just as with my last example here, I did an arbitrary matrix, A, B, C, D. That's what a generic vector in M22 looks like. We want to choose a generic arbitrary vector in V. That's step one. So now, so set up the augmented matrix corresponding to the equation I guess it'll be x1 times v1 plus, I used an x. Let me use different letters here. A1 times v1 plus a2 times v2 plus a sub k times v sub k equals x. So when you write this down, we've got the linear combination of the v's on the left-hand side, we have our arbitrary vector x on the right-hand side. That will correspond to a linear system, and that will then give us an augmented matrix. If the system is consistent for all x, meaning for this generic one that I chose here, then span of capital S is equal to V. Right, so if, and this is still part of 3, if the system is inconsistent for some x, then span of S is not equal to V. So these are the steps to go through. This doesn't work every single time, but for all the examples that we see today, this process is going to work. So if we can solve the system, then we conclude that the span is equal to V. If we can't solve the system, then we conclude that the span is not equal to V. And I'd rather you not memorize these steps right here. What I really want you to do is understand why this is the right process. Right? The question is, if you want to have a spanning set, that means that every vector can be expressed as a linear combination of the elements of S. That's what you want to remember, is this equation right there. Right? If span of S is equal to V, then this equation can be solved for every choice of X. So, okay, so let's try some more examples. So here's a spanning set for M2 sub 3. Right, so we looked at M22, and I gave you an actual spanning set. We went through the process. We showed that it actually was a spanning set. Now, I want to just think about, if we wanted a spanning set for M23, I want to just write down the answer here. Let's think about what a typical matrix in M23 looks like. It looks like A, B, C, D, E, F. Okay, now, what is this matrix? This matrix is A times 1, 0, 0, 0, 0, 0, plus B times 0, 1, 0, 0, 0, 0. Hopefully you can see where I'm going with this now. Plus C times 0, 0, 1, 0, 0, 0. Plus D, there's going to be 6 of them, right? 0, 0, 0, 1, 0, 0. Plus, sorry, I ran out of room here. I'm going to write the last 2 down below. Plus E times 0, 0, 0, 0, 1, 0, plus F times 0, 0, 0, 0, 0, 1. So notice now, an arbitrary element of M23 can be expressed as a linear combination of these 6 matrices right there. That tells us that that collection of 6 matrices is a spanning set. And we should be able to generalize this for all of the M's. And by the way, this is obviously not, well, this is not the only spanning set, but what we've done is we've shown that this is a spanning set. So more generally, in M sub Mn, let E sub ij be the M by N matrix with 1 in the ij position and 0 elsewhere, then the span of the set of all Eij, so I'm being a little loose here, take all possible E sub ij's, right? So there's going to be M times N such matrices, right? That's equal to M sub N. Okay, so there's one example of a spanning set for M sub Mn. In particular, then, the following matrices right there, these 4 right here span M22, right? So we had a spanning set in our last example for M22. Here's another spanning set. Every matrix in M22 can also be written as a linear combination of those 4 right there. Okay, so let's try some more examples. How about a spanning set for D sub n? Remember, D sub n is the vector space, the subset, the subspace of M and N, consisting of all diagonal matrices. Well, let's see. So what does a diagonal matrix look like? It looks like A1, A2, dot, 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 all the way down to AN along the diagonal, and zeros everywhere else. So what's an obvious spanning set? E11, E22, E33, all the way down to E and N, where, as we defined just a minute ago, E11 would be the n by n matrix with a 1 in the first, and the 1 position, and zeros everywhere else, right? That one right there. And then E22, right, has a 1 in the 2 position and zeros everywhere else. So if you go through here, it should be fairly clear that this set right here is a spanning set for the set of all possible diagonal matrices. Okay, next example. And so let's move on. We've been talking about matrices. Let's move on to another choice of vector spaces. So this question is the set 1 plus x, comma, x plus x squared, a spanning set for, so here now we're dealing with polynomials. And the question, is that a spanning set for p sub 2? Can every polynomial of degree less than or equal to 2 be expressed as a linear combination of those two? And for the answer, well, the answer is no. And so let's see why. So the solution, consider the following: a times 1 plus x plus b times x plus x squared equals 1. All right, so what's going on here? If the answer is yes, then every single polynomial in P2 can be expressed as a linear combination of these two right here. Now, the constant polynomial 1 is a polynomial of degree less than or equal to 2, and so in particular, then, the polynomial 1 needs to be a linear combination of these two polynomials. And so let's see what this would tell us. This would say that, so I'm going to multiply things out. I'll have a plus a plus b times x plus bx squared has to equal 1. So all I did was distribute and join things together here. Now, if this equation is going to be true, that would tell us that a is equal to 1, a plus b has to equal 0, and b has to equal 0. Right? Why is that? Well, because the constant terms have to match, the degree 1 terms have to match, and the degree 2 terms have to match. Well, if b is equal to 0, and we come back up here, that would tell us then that a has to equal 0 as well. So now we've got a problem. We know that a has to equal 1 and a has to equal 0 at the same time. That tells us that this system is inconsistent. I didn't even bother setting up an augmented matrix. It was easy enough to just solve or see that the system was inconsistent. So inconsistent. And so what that tells us then is that the span of those polynomials, 1 plus x and x plus x squared, is not equal to P2. As soon as we find one polynomial that is not in the span, we're done. Okay, so I want to do, let's go there, 2 more examples. So the next one, let's let t from R3 to R2 be the linear transformation given by, so here's our formula, t of the vector x, y, z equals x plus y and y plus 3z. So it's easy to check that this actually is a linear transformation. We're not going to go through the process here. We'll just accept that it is a linear transformation. And what I want to do, I want to find a spanning set. Lights went out again. Okay, lights are back on. So I want to find a spanning set for the kernel of T. Remember, and I'll just I'll say it here. So recall the kernel of T is the set of all x, y, z in R3 such that T of x, y, z equals the 0 vector, which in this case would be 0, 0. Okay? All right, so what do we do? Well, let's just look at the standard matrix just to make life easy. So the standard matrix of our linear transformation is going to be 1, 0, 1, 1, and 0, 3. So what we then have is this situation right here, 1, 1, 0, 0, 1, 3, 0, 0. So vectors in the kernel correspond to solutions to this homogeneous system right here. And this system is, well, it's almost in reduced row echelon form, so let me do one quick row operation here. 1, 0, minus 3, 0, 0, 1, 3, 0. Okay, so now in reduced row echelon form, we've got one free variable, so let's say x3 equals t, and then let's see, x1 equals, it'll be 3t, and x2 equals negative 3t. So solutions to this system look like this: 3t minus 3t, t. Right? So if you're in the kernel of this linear transformation right here, what that means, right, is that when you plug in x, y, z, the output is going to be the 0 vector. Elements in the kernel look like this. And, okay, so fine. That's going to be t times 3 minus 3, 1. So every single vector in the kernel of t is of the form t times this vector right here. What does that mean? Well, what is that? That's a linear combination. Every vector in the kernel can be expressed as a linear combination. And so the kernel, or let's say, take like this, the set consisting of a single vector 3 minus 3, 1 spans the kernel of T. All right, let's try one more example. So let's let, sorry, yeah. I spaced out for a second. In P3, let W be the set of all polynomials now, what do polynomials look like? All polynomials look like a plus bx plus cx squared plus dx cubed. That's the collection of all possible polynomials. And what I look at is some restricted set, some subset of P3. So such that a plus b plus c equals 0. So W is the set of all polynomials that satisfy these conditions here. Two parts to this problem. So first, I want to show that W is a subspace of P3, and part B, find a spanning set for W. Okay, so for part A, right, we want to apply the subspace test. So remember, it needs to be non-empty, so note that the 0 polynomial satisfies these conditions right here. 0 plus 0 plus 0 plus 0, or well, 0 plus 0 plus 0 is equal to 0. So note that 0 is in capital W. Right, so it's non-empty. So let's let P of x, that will be A plus B x plus C x squared plus D x cubed. Q of x is going to be, I need to use some other symbol. How about A bar plus B bar x plus C bar x squared plus D bar x cubed. So I'm calling the coefficients of the second polynomial A bar, B bar, C bar, and D bar. And I want these to be vectors in W, polynomials in W. So let these be in W. So what does that mean? It means that A plus B plus C equals 0, and it means that A bar plus B bar plus C bar is equal to 0. So now, I want to look at constant times P of x. I want to show that W is closed under scalar multiplication. So let's say R times P of x is equal to, well, that'll be an RA plus RBX plus RCX squared plus RDX cubed. And RA plus RB plus RC is equal to R times A plus B plus C, which equals R times 0, which equals 0. So what I just did, I created this polynomial, or looked at this polynomial R times P of x, looked at those coefficients, added them together, and got 0. So R times P of x is in W. Also, what we just did is show it's closed under scalar multiplication. So also, P of x plus Q of x, let's see, if I add those polynomials together, what I'll have is A plus A bar plus B bar x plus C bar x squared plus D bar x cubed. And now, what I'd like to do is verify that this polynomial P of x plus Q of x lives in capital W. To do so, I need to add the first three coefficients together, verify that I get 0. So let's do that. A plus A bar plus B bar plus C bar. That's equal to A plus B plus C plus A bar plus B bar plus C bar, which is equal to, well, this part right there, that's 0, and this part right there, that's also 0, right? Because both of our polynomials started off in capital W, we know that these each sum to 0. Okay, so P of x plus Q of x is in, or lies in. We showed that it's non-empty. We found a vector in there. We showed that it's closed under scalar multiplication and under addition. So by the subspace test, W is a subspace of P3. Okay, so now let's do part B, right? We want to find a spanning set for our subspace W. So to do that, so let's choose, let me call it P of X. So let's choose P of X equal to A plus BX plus CX squared plus DX cubed. All right, so we want to choose an arbitrary polynomial in capital W. So since one thing we know now, A plus B plus C has to equal 0. So since A plus B plus C equals 0, we have that A is equal to minus B minus C. And so we can rewrite our polynomial P of X as negative B minus C. Just replacing A with negative B minus C, plus BX plus CX squared plus DX cubed. And then I can write that as negative. How do I want to say this? Negative B times 1 minus X minus C times 1 minus X squared plus D times X cubed. Right, so I just did a little arithmetic. I joined the stuff involving B in one part, the stuff involving C in another part, and then the stuff involving D. So what have we done? We've shown that our arbitrary polynomial P can be expressed as a linear combination of these three polynomials right there. So W is equal to the span of 1 minus X, span of the set of polynomials 1 minus X squared, and X cubed. All right, that's enough for today. I said this a little while ago, spanning sets were difficult for me when I first learned them. I hope that this clarifies things. I hope it's not too difficult for you, but you do need to think about what the definition, you need to understand the definition, right? Spanning sets are a little bit confusing. They're one of the harder concepts. Notice I spent 2 days talking about spanning sets, and that's in hopes that it's going to somehow sink in and hopefully it won't be as difficult for you as it is for me. Okay, see you next time.